Right. So my name is Andrei Marinica, as Grigore said. I'm from MultiversX. And today I want to talk to you a bit about our smart contracts, because that's primarily what I do. Not only the VM, but also the tools for developers, because that's very important, right? And we're going to go from specification to execution. And I'm going to give you a broad introduction about what MultiversX is, for those who don't know. Maybe some of you do. Then objectives. And we're actually, I think we're going to go a bit in reverse. I know the title is from specification to execution, but the story flows better if you start with the execution, and then you figure out how a specification should look like. So we're going to go through how contracts run and then how they interact with each other. So without further ado, what is MultiversX? So in the past few years, at MultiversX, we've been building this blockchain, which is very scalable. And to achieve that, we use state sharding and proof of stake and all that good stuff. And we also have the Eagle token. Maybe you've heard of it or own it. But even more important than the blockchain is that we want to onboard the next billion people onto Web3. That's what we also always say. And to do that, it's not enough to have a good blockchain. You also need to have a large ecosystem of very nice, very friendly, very useful applications for people to use. So we've diversified a lot, and we're building all these products. For instance, X Portal is mobile app. I don't know if you've tried it. It's a bit like Revolut, but on the blockchain. And we're gonna see a lot more from us. Like X Fabric will be for companies to set up their online Web3 presence, and X World is our endeavors in the metaverse. And there's many more. Like we have NFTs and the bridges and so on. So I won't go too deep into this because it's not what the discussion today is about. I'm going to talk to you a bit more about how you create an ecosystem, a big ecosystem, what your objectives should be, and what you should strive for in order to get a big ecosystem. And the point is, you want to have a lot of products that people use, and for this, you have to have a lot of developers that develop on you. And for it to be usable, it needs to be fast, obviously. So that's where we started from in the first place. You need determinism because otherwise blockchains don't function. And you need safety because you're working with people's money, right? So, and you need safety in the primitives, but also then how you combine these primitives into smart contracts, and then smart contracts into bigger systems, and so on. And a subject that is actually very dear to my heart is composability. In order to have the ecosystem grow, you need for people to be able to build bigger things out of smaller things, because otherwise you'll keep reinventing the wheel, and you never get anywhere. And composability is actually quite tricky to achieve. Lego is a brilliant company because they achieved that, with the toys. It's not so easy in software sometimes to have composability that is usable and safe. And I'm gonna discuss a bit about that. So let's start with the basics. How we run our contracts, and how they function. So I shamelessly stole this off the internet. We use Wasmer. So first off, you need a high-level language to write your smart contracts, and nobody wants to write in assembly. And for us, it's Rust. So out of all of these, Rust is the one. And then we compile it down to WebAssembly, which is this very portable sort of assembly language, very friendly. I personally like it very much. And the nice thing about it is that you can have very deterministic, very stable execution on very different machines, different environments. Again, you need this to reach consensus. And for this part, there's many ways to interpret WebAssembly. Like you could have interpreters, and we tried a few of them, but in the end, we ended up using Wasmer. And what's so cool about Wasmer is that it compiles them down to machine code, which means you're actually running them at machine native speed, which is an order of magnitude, maybe an order and a half or two, better than the best interpreters. It's simply, you can't beat that. And you can't see it very well, but the cool thing is you can then compile to all these kinds of different architectures. We support Linux, and we're working on ARM now, and yeah. So this is kind of the big idea. Now, and I don't know how familiar you're with WebAssembly. I won't give you a lecture on the format. And of course, you can't read because font is very small, but you have to trust me on this one. So this is very simple contract. There's a factorial, and this is WebAssembly. This is assembly. Just imagine it. And just a point I want to make. So WebAssembly is a binary format, but it also has a text format, and it's called WAT, and it's very useful to investigate the contracts, what they do, and it's actually quite readable, which is unusual for assembly. And you can. This is normally what you have in production, but I just wanted to make you aware that you can also build with like debug symbols, and you can have a lot of artifacts from the higher level language in the WebAssembly, which is nice. And it's very simple to understand conceptually because it has imports and exports. Like one side stuff that goes in, and the other side stuff that is produced. And up here you can see usually the imports, and this is the environment interface. So these contracts they run in an environment, in a sandbox, and this is basically the interface with that environment, and this is what they produce, like the functions that they offer. And this sandbox environment is very important because it is part of that kind of predictability that we want out of contracts. And it's stuff like give me this argument, give me these tokens that I received, push these results back, blockchain info, and a thing called managed types that I will talk to in a moment. And then the endpoints are what the contract offers to the world, like a constructor and then all sorts of functions. Right, and now the thing about managed types, this is a bit of an innovation that we did because it all started. It comes from like there's a few reasons why you might want something like this. So when we first started the current VM, we figured out that big integers are a problem, and as you might know, on EVM they're a big problem because overflows happen all the time. So we wanted to have native big integers from the beginning, and so what we said, okay, why not make a heap, sort of like a heap, a structure, a map in the environment that with values that the contract doesn't see. You just pass some handle, like pointer, to the contract, and you just work with them, and you have sort of like native arithmetic in the contracts without having to re-implement in every contract all the arithmetic, all the rules, and so on. And then we expanded it to just random string series of bytes. And now, for this reason, we don't need an allocator anymore because the environment takes care of it for ourselves. So it's like a virtual heap. And what is very cool about it is that it helps write very small contracts. And just to point this out, I'm not expecting you to, read WebAssembly, but the same way you have like this elementary instructions in assembly. Because you are using the environment, you can have the same elementary instructions for like big ints. You can add them as you would add like just regular to integers. Oh, sorry. And this is how you get contracts as small as this one is 600 bytes and it's like 100 lines of assembly. You can almost read in assembly directly what it does. And this is very cool, not only for speed and performance, but also when you start to want to reason about contracts. The fact that they're so small gives you a bit of more of a direct access, so the assembly is a bit closer to us than would normally be. Yeah, and this is the function that created that. So you actually also have high level functions and languages. Rust is creating a quite nice environment to develop in. Right. So now that we have contracts that run in our in our VM, in our environment, we have to talk about how we compose them, because rarely is it useful or very interesting to have a single contract. Most big dApps have at least several contracts. And I mentioned very early in the presentation that one of the key innovations that we have is sharding. So the MultiversX blockchain is a sharded one. Now shards are like separate blockchains that work together. And the important part is that one shard does not know about the data on the other shard, because that would kind of defeat the purpose. Which means whenever you have two contracts in different shards that have to communicate with one another, they have to send messages across these shards. And in general, so you have two contracts, you want them to communicate with one another. There's two ways. You could do it synchronously, like Ethereum does, but that only works if in the same shard. And then contract A can call contract B and get the data out of it, and it's atomic. It's a lot easier to use. But if it's not into that shard, you don't have it because it's simply not there. And then for synchronous calls, you have to send actually messages. You have to wait for a few rounds, and then you get a response back. So unfortunately, cross-shard atomicity is something under research. I don't know how it's, if we're going to have it when, would be interesting. But for now, contracts actually have to handle their rollbacks and stuff like that if it happens cross-shard. So that's one aspect of, yes, please. They are deterministic. It can't. Because the protocol handles the callback. So the callback will arrive one way or another. The contract can choose to ignore the callback, but the callback will come. It cannot be stopped. And also there's a mechanism. So if you launch, we call it asynchronous. They're not necessarily synchronous. They're more like you don't know when they're going to execute on the other shard. So they don't, I mean, they're running away in parallel because the shards you can think of as running in parallel, but it's not a synchronicity in the classical sense. It's more like you don't know when to get the answer back. There is a mechanism. Once you launch an asynchronous call to another shard, it is guaranteed to execute. So they cannot get lost, these messages. They will always execute. The programmers don't see. And actually, that's another nice thing about this environment, that the interactions with the other contracts are also baked into the environment. So the contracts don't have to know, and they cannot know actually how these interactions happen. They just request stuff from the VM. VM, please, tell this contract I love him. Stuff like that. Right. And this is graphically how it happens. So normally a user will call a contract, and the contract will launch a message. This is on the other shard. This is shard 1, this is shard 2, and then you get the response back. Yeah, and that's how you can have some composability cross-shard. So this is one type of composability. As you can imagine from this setup, having ERC20 style contracts like this can be a nightmare, because imagine you have a contract on one shard, you want to send some tokens to shard 2, but then the tokens itself, the contract is on shard 3. So it becomes a mess of cross-shard communication. And this is the reason we created the ESDT tokens, electronic standard digital tokens, and we baked them into the protocol. We did this because this way the protocol can just send them from one shard to the other as like packets. You just send the token. You don't have to write in a contract somewhere. And so they're native. That also makes them kind of fast, and it's also convenient because the contracts also don't have to, worry so much about them. And you also can't have like hacky scam tokens that have some funny allowance or some non-standard behavior that's stealing your money, because they're baked into the protocol, so you can't really tamper so much with them. And we also don't like allowance, because allowance is not nice. And they can be semi-fungible or non-fungible, and you can transfer multiple of them at once, which is also very convenient. And a thing that is not very obvious to people is that these ESDT tokens are actually also a form of storage, because if you have a semi-fungible token or NFT, you also have a data field there that is the metadata of the token that you're sending. And you can, and we're actually playing with this a lot sometimes. When you want some sort of storage that is not tied to a certain shard or to a certain contract, you can have bits of storage that can float around from one shard to the other, and you can sort of get some sort of decentralized, cross-shard storage with them, which is quite interesting. And I want to talk to you about another very interesting type of composability. So these external review contracts, not many people know about them. How are we at the time? It's fine. Okay. Okay. Not many people know about this. So it's this thing that we have with contracts. We're very obsessed with keeping them very small. So we love small contracts. The small contracts are fast and all that. But when you write a smart contract, you want often a lot of view functions, because the contract has a storage, and you might not want to scramble to the storage data off chain. You might want to just call a function, query it, and get some nice report out of it. And normally the more view functions, the merrier. But the problem is also the more view functions you have, the bigger the code is, the bloatier it is. So I think that we figured out to reduce contract sizes was, well, how about taking all the view functions that are very rarely used on chain and putting them in another contract. And the thing is, on MultiversX, and I think most blockchains, contracts can read from storage of other contracts directly most of the time. And so we thought, how about, we take this contract implement. Thing is, you also don't really want to, as a developer, to write too much. So writing the code in separate contracts and then dealing with this kind of thing in the manually, can be a bit of a hassle. So what we decided to do was, well, but how about you write a single smart contract, and then you have a build process. You configure it, of course, and you have a build process that produces some of the code it puts into one contract, and some of the code it puts into another contract. And we call it a multi-contract build system. And you can do a lot of things with that. This is what we use, mostly what we use it for. So this is the first thing I want to point out. Not always when you write a smart contract, what you end up with is one smart contract. You might end up with more, or as we will see, several tools. Okay. Yeah, normally whenever you deploy a smart contract, it will be in the same shard as you. So if you're the deployer and you deploy these two contracts, they will automatically be in the same shard. So yeah, they have to be in the same shard for this to work. Okay, and I'm just gonna put this idea out there, a wild idea. You could, in principle, also use it to version your contract. So you write a smart contract and you say, well, but this function is in version 1 and this function is the version 2 of it. And you might have that. But this is still ongoing research, so I'm just putting it out there, and I'm not gonna, I will not develop further yet. If you want, we can discuss afterwards. Now, I did talk about on-chain composability, and for most people, when you say composability in blockchain, that's gonna be it. Like, yeah, okay, sure. How can stuff on the blockchain communicate with one another? But thing is, dApps in the real world are much more than just some smart contracts on the blockchain. You have a lot of applications around them. You have a lot of services. You have a lot of stuff going on. And what we're trying to do, and a very simple example of this is even just testing a smart contract, right? You don't want to keep deploying your smart contract over and over again. There's people who do that, but it's a bit counterproductive. Usually you just want to have some local simulation of the blockchain, just run it locally, like you would do a regular program. And you can even in principle do it with real data from the blockchain if you download it. Like, I want to interact with this pair, right, of an exchange. I want to download the data and I want to interact with it. Okay, so let's think a bit. How can you run a smart contract? What are the ways in which you can run a smart contract? And this is not an exhaustive list. So of course you can run them on chain, but then you want to run a test. You can also run it locally with a real VM, but with a mock blockchain. You could also run it locally in principle with an entirely mocked, entirely artificial, so to say, environment. And we actually use it for debugging contracts. But here's the deal: you can do some sort of a hybrid thing between them. Imagine we take the environment from a smart contract, and instead of tying it to either the real blockchain or to a simulated environment, we tie it to a blockchain API. So we query locally a contract, but the data comes from a real blockchain. If you're confused, maybe this helps. So you have a smart contract, you have the standard smart contract interface, and yeah, this is like the regular route. I have a laser, right? No, this. I'll just point. Right. So this is the regular route on chain, and this is maybe how you mock. This is how maybe you mock it. This is maybe how you simulate it. But you could tie it to a blockchain API and then get real data from a blockchain. And what you've done basically, you've been running a smart contract. Uh-oh, I pressed something. Okay. You're basically running the smart contract locally. It's like a regular program, but you're querying data from a real blockchain. Well, you can't write it like that. Yeah, you can write it locally if you want. You can't write like that data, but you can query it. Right, and now think of what this means for our external view scenario, because we don't even need to deploy this contract anymore. This can be just like a service. And yeah, between them, you don't actually have to have some on-chain stuff going on, because you don't have to run it on-chain, right? You can just run it on a local machine and just query the API for the storage. And this is very important, because what we've done is we've written a smart contract. But look, now we have not only a smart contract running, but now we also have a service that's running on top of that smart contract, giving us data and processing from the same code base with the same functions. So yeah, what does it mean to write a smart contract? Because apparently it's not necessarily a thing that runs on the blockchain. It's more like a specification for how to interact with the blockchain, both on-chain and off-chain. So yeah.
But basically, you can use the external view contract as a way to have the storage or the state read from the blockchain, but not to deploy it on the blockchain itself.
Yeah. This is just like for reading data as an example. In principle, you can. We're also working on ways to make it easier to deploy contracts. So you've written a contract and you want to have automatically something for you to help you deploy them, or handle like versions, different versions. So this is like the simplest sort of scenario. Yeah. So if you have, and you can do that. We are building some sort of interactors. In principle, you can do that. Yeah. I mean, not right now, but it's not very difficult to pull off.
Also, if I may, I believe that the smart contract role is also for auditing purposes, right? Because all the transactions, all the interactions with it are there.
Yeah.
While off chain, you can do other.
Yeah, I actually have a slide about this. So you can actually, in principle, you could write invariants like a function that is an invariant. You can write it actually in the contract and never actually deploying it to blockchain, but using it as a verification tool. Yeah, I have something on this. So yeah. So I want to talk just really quick about, so how do we specify smart contracts? Well, we use Rust, obviously. But what I want to point out is that there's not just the imperative side of it. Actually, we write. You could say that we use a pretty modified version of it because we have all these procedural macros and all these embellishments. And I would even say that they're a bit of a descriptive layer on top of the actual programs, because you can specify like how the storage looks like. This is pretty descriptive, or what the inputs are and what the outputs are. And then of course you get an API out. So out of the inputs and the outputs, you'll have like what goes in, what goes out, what's the layout of the structures that you're interacting with. And this API, yeah, you can't see it very well, but it's just a JSON, so it's platform independent. And thing is, you've written smart contract, you're getting the API, which is not Rust or anything, and then you can plug it into a TypeScript project and get your types there. Maybe you can plug it into the Explorer directly, and then you have a nice interface. And yeah, a little a side note here, if the contract is in Rust, and if you're writing tooling that is also just Rust, you don't actually have to go to the API. So we have an intermediate level called proxies, where you can just query contracts and integrate it. And this is something I wanted to touch on, because basically the contract is like a black box, and it has a specification. The ABS is sort of a specification. It's not a complete one, but at least the inputs and the outputs. And it's very helpful in writing tests, because you can query it as if, and send transactions as locally as if it was just an object on your disk. And then a thing we have is called interactors, again plugging the blockchain API behind that, and then you can interact with a contract on chain as if it was an object local to your machine. So with all of this, my point is we're trying to kind of blur the line between what is on chain and what is off chain, and make it a big nice system with a big nice coherent specification. We can do better. So invariance is what we mentioned on earlier, and it's probably going to be a pretty cool thing to do, to write an invariant function, storage consistency checks, and migrations. Yeah, I think we'll close on end. So last thing on the list, formal models. There's Virgil and the team here. They're writing the semantics for our VM. It's already runnable. I won't dwell on it too much. But what I want to point out is that once we have this executable semantics, it's pretty easy to plug into our whole stack, into our big sandwich. There's layers in it that can be replaced by this executable semantics. And another thing I want to touch on, also Virgil worked on this. He created a specification for a contract called the multisig, and built a lot of proofs around it. Now, this is a bit trickier to integrate because it's a bit higher level, and you would actually have to integrate it somehow with developer tools. That's kind of what we're aiming for. This is a bit farther away.
Through the API.
Mm-hmm.
Through the API eventually.
Yeah, part of it would be the ABI, but it goes much deeper than that, because the ABI is just like sort of the outer layer of the contract, is like the shell. Whereas with this, you want to go deep inside it. But yeah, in an ideal world, we have this sort of specification language, and we produce maybe contracts directly out of it rather than Rust, maybe, or And so, just a few takeaways. Specification execution are pretty separate, and as you can see, they come from different sides, and it's good that they are far apart. And a bit of more of the denotational approach and more descriptive stuff always helps with tooling. And also formal models and traditional systems can be friends. So thank you very much.
I can confirm that among all the clients we have at Runtime Verification, the Elrond team, MultiversX team, is the most pleasant to work with, because first they really understand formal methods and formal verification importance of this, and they want it. Others, we have to explain them why they're important. So it's a real pleasure. So thank you. Questions?
Yeah.
We have a few more minutes.
We're sometimes frustrated that we can't do more formal methods because we don't have time, but hopefully we'll be getting there.
Until somebody asks a question, I would say that what it would be really nice is to have a K client. Once we define the semantics of the
yeah, so about the thing with the K client, actually we also want this, but we don't want to tackle the task head on. That's why we have like these small components, and we're trying to make them modular so we can replace them one after the other. And maybe at some point it will be like the Theseus ship, you know, you replace enough so that it's a new thing altogether. So yeah. And actually we've all so traditionally we've only had one implementation of our protocol, but we're getting close to actually having a second VM written in Rust that's kind of the same thing. For now, it's only part of the VM and it's used for tests. But in principle, I think we're getting close to having and if you can replace the VM, then maybe other parts too. So yeah, sorry.
I like the idea of having local smart contract, let's say.
Yeah.
And I think it's very similar to off-chain computations that are, for example, ZK Sync, or where you compute, where you run your computations and then you post them on chain, and the contract verifies that the verifier actually verifies the computation.
Yeah, I did not touch on ZK stuff. Probably there's a chance that what we'll do at some point we might be adding at some point some cryptographic primitives for ZKs used in contracts, like in the
demonstrate the execution of the local smart contract. This is the idea, I think.
That would also be nice.
Game.
So, yeah, once we have the K semantics for our VM, then you can in principle also, you know, with a system that Grigore presented, actually generate proofs that a certain contract behaves in a certain way. And this is actually quite a nice thing to have, and especially since contracts work in this very sandbox, very controlled environment, it makes a lot of sense. That you don't have to recompute it every time. You're guaranteed to get the same result.
I want to run, for example, locally a set of smart contracts and just post a proof on chain. And that's the idea everybody chases and nowadays in blockchain. So it would be awesome to have a
we'll come help with the implementation. In that case, you're invited.